Guess we should go ahead and get started. Anybody have any questions before I do get started? Oh, I see it now. I have locked the documents for the lab that's due tomorrow. Yes, actually, I have. Joseph asked. Sorry if this was asked already, but are you able to unlock the documents for the lab that's due tomorrow? Yeah, that shouldn't be a problem. I assume you're talking about the turn-in area for the lab for tomorrow. Is that accurate, Joseph? Let me try to look in there now. Well, I got you here. I might have just accidentally changed it with my mouse button by accident, but we'll see. So yeah, that would have been last week. And are you talking about Lab 7 nonlinear graphing? Okay, gotcha. Looking at that right now. If you click on the nonlinear graphing 1, Lab 7, there's documents in the actual turn-in area. You can click on those. Are those not working? And then the other thing is, let me go back and look at the module, see if that's part of the issue. I'm looking in lab module for week 8. I assume that's what you're talking about. And I've got lab 7 time versus distance. Oh, okay, I see. I don't know why that's not there. Nonlinear graphing, and there you go. If you'd look at that and see if I got you, see if you can see those now, Joseph, that would be helpful. If not, just let me know and I'll make sure I fix it better when I'm finished here. Anybody else have any questions? Appreciate it. Sorry, I don't even know how that happened. They were literally just unpublished, and I don't know. I mean, I can't imagine why I would do that unless I just did it by accident or something. So sorry about that. But it did bring up a special thing. My brother called me today because he don't like to wait till the last minute, and told me he has a doctor's appointment that he needs a ride for tomorrow. So I'm going to have to record your meeting for lab some other time. So I will not be holding lab tomorrow at the normal 10 a.m. like I normally do, or 11 a.m., whatever time I normally do it. I'm not going to be able to do that tomorrow. I will post it sometime tomorrow. I'm just not sure when. So obviously, if it goes past where I post it on Thursday and end up posting it Friday, then I'll make sure the lab's not due until midnight or 11:59 p.m. the following Friday. So I just want to let everybody know that I will not be doing my lab live session at the normal time tomorrow. So don't bother showing up for that. If you have questions, by all means, let me know. And I might even do this a special lab that makes it a little easier. We'll see. So, anybody else have any questions? Michelle, like that. That's cool. Well, I did want to let you guys know and remind you to go ahead and chat me your first and last name if you haven't done so already. It looks like everybody has. I've got about 12 people in here. That's good. So I want to go ahead and get started with chapter 8. Last time we went through chapter 7, and I showed you all the line integrals and all that good stuff. And then chapter 8, I jumped into talking about conservation of energy, and I discussed a theorem that exists. And this theorem is super helpful. I didn't learn it until I was actually like in electricity and magnetism. That's when you learn this theorem that's so helpful. But it's actually really helpful in the mechanics world too. But basically, it's this: if a force is conservative, then everything I'm about to say is true. And not only that, if any one of these things is true, all the other ones are true too. So you can use each of them as a way to show that F is conservative too, meaning F is a conservative force. And I went over that ad nauseum. It's on the video. The video, of course, took almost 2 hours instead of the normal hour and 20 minutes. And I cut it down quite a bit, but it's still pretty long. So you can sort of just skim over that part. But the key thing is, I posted in an announcement what the key parts of what you're supposed to learn from that theorem are, is that, and I'm going to miss some of them now, so I want you to go back to that announcement to make sure. But basically, the idea is this: hey, if a force is conservative, you know that it has a scalar potential that can be used. If a force is conservative, you know that the integral from A to B, in other words, the work done by against the conservative force or by the conservative force in going from point A to point B, is equal to just a function of B minus a function of A, and is independent of the path. Okay, so that's also another test that you could use to figure out whether the force is conservative, because if you really did integrate from A to B to calculate the work done and you found that it was independent of path, then you'd know that that's a conservative force. Also, if you do the work in any closed path, so you start at A and you do all this crazy stuff and return to A, that work should be zero. Uh, in addition to there existing a scalar potential function that you could use, we also know that that force can be given by the negative gradient of that scalar. So those are sort of the key big topics that you're supposed to get out of that theorem. But the main thing is knowing that theorem exists tells you all this cool stuff. There's another thing about exact differential equations that I didn't cover that clearly because I just can't give you all the information, and plus I'd have to look it up myself because it's been so long since I taught or took differential equations. But there's a differential equation process that you do when equations are exact, and the scenario in which a function is an exact function and makes an exact differential equation is related to this conservative force thing. So just want to make you aware of that. I then went on and derived a couple of scalar potentials. Specifically, one of the things you're supposed to learn from that theorem is that there is a way, once you know a force is conservative, there's a way to actually calculate what the scalar potential is. And the way you do that is you calculate the work done in going from, let's say, point A to point B, and that's the work done by the conservative force. So you take that force that you have been told is conservative, or that you've tested and proven that it's conservative. You take that force, calculate the work done in going from point A to point B, and you take that work, multiply it by -1, and set that equal to the change in potential energy U evaluated at B minus U evaluated at A. Now, as luck would have it, it turns out that the scalar value of a function isn't that of that potential energy function isn't that important. What really is more important is stuff like the derivative of that function or the difference of that function at two different places, stuff like that. Because of that, you can add any arbitrary constant to the potential energy function, and it doesn't affect anything negatively. Because of that, you can assume, for instance, when you calculate uh, the work done by the conservative force and then you multiply that by a negative, you can set that equal to U evaluated at B minus U evaluated at A. And you're allowed to just say, okay, well, I'm going to take the condition that the U at A is actually equal to zero, and then that allows you to immediately get U of B, and you can figure out from that what the function of U, the potential energy function, looks like. In doing that, I was able to derive the function for the potential energy of the gravitational force near the surface of the Earth, and that's just U is equal to M times G times Y. Additionally, I did it for the gravitational force that you use, Newton's law of gravity, when the radius or the distance from the center of the Earth is comparable to the radius of the Earth. And that function happened to have a negative sign in it, and that's important. You've got to have that negative. But that potential energy function is U equals negative G, the gravitational constant, times big M, the mass of the planet or whatever, times little m, the mass of the other thing, divided by R. So that's the potential energy function. In that case, though, we chose the U potential energy set equal to zero at R equals infinity. So you don't really ever let R equal infinity. Of course, you just sort of set the limit as R approaches infinity, and you let that be the scalar function at that infinite value. And when you get that, you set that equal to zero. So you've already got an established zero of potential energy for that function. And you could also do, as your book did, you could treat the work put into compressing a spring as 1/2 kx squared, you could treat that as a potential energy function as well. So those are the three things I came up with, and then I gave you an equation for conservation of energy that I recommend you use. Now all I'm going to do is work a bunch of examples relating to these potential energy functions and to this conservation of energy. So to that end, let me go ahead and share my screen. Feel free to ask me questions at any time. I feel really bad. I get up here and I start talking and teaching, and nobody asks me any questions. And I'm hoping that I'm doing a good enough job where y'all are understanding everything, but I'm really scared that I'm sort of blowing you away, and I don't want to do that. So please slow me down, stop me, whatever it takes, so that you can get the help that you need on this. So by all means, do that. So this is what my notes are starting off with. You see, I've went back and written down what we found last time, specifically the potential energy function for gravity. I called that U sub little g because that's when we use m times little g for the force of gravity. In that case, the potential energy is just m times g times y. And I said where y equals 0 is a matter of choice because you can put that 0 of y anywhere you want because it's just like moving the origin to different heights. And you can always set up a coordinate system anywhere you want and put the y equals 0 origin anywhere you want. So that's why that's there. You can see the next equation over is u sub big G because that looks like the gravitational constant. And that's the one we got for Newton's law of gravity. And notice the negative sign. That's going to come in handy in a second. But I reminded you that UG is equal to 0 as R approaches infinity. In other words, we already set in some sense arbitrarily, we already set the potential energy equal to 0 at R approaching infinity. And then I mentioned what I just mentioned to you guys, the potential energy of the elastic force, which is, Hooke's law, F equals negative kx. The potential energy of that is 1/2 kx squared. I tend to think of that as a potential energy on occasion, but I also think of that as the work done in compressing a spring, but I also think of it as the work done in stretching a spring. And sometimes I even think about it as the energy released or the energy lost. It's the energy released when a spring is allowed to expand on its own with a mass in front of it, and it's the energy lost when an object comes barreling towards it, hits it, and compresses it. So I can think of that as U, as W, or as E. And I said that because you see down here I have U, I have W's, and I have E's. So that's where that comes into play. Now, as I told you, the potential energy, the conservation of energy function that I use is U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Now, from symmetry, I could have put plus E in over here after the work in function. I could have put plus E in, and that would be fine as well. It's just I made this up before I had a big picture of everything, but it turned out that it worked really well. And in fact, I invented it or discovered it or made it up or whatever when I was still just a student tutoring taking this exact class. And it worked so well that I've continued using it for my tutors, whether it be a high school physics class or a college physics class or uh, even technical physics and stuff like that. I've always found this pretty useful. The key thing to understand here is that one, you want to make sure you have exactly one term for every type of energy that you're dealing with, and exactly one. So it's not only important that you include each type of energy, but that you not include it more than once, because then you'd be double counting, and that would be a problem. Not only that, it's also important to understand that each of these terms, it looks like you have 3 on the left and 4 on the right, each of those terms represent possibly more than one term. So, for instance, kinetic energy, you know of that as 1/2 mv squared. But in reality, you can think of that since v squared is equal to vx squared plus vy squared plus vz squared. You should think that the kinetic energy could be 1/2 m times v sub x squared. That's one term plus 1 half m times v sub y squared, that's the second term, plus 1 half m times v sub z squared, that's the third term. And that's just for a point particle that's translating or moving in space. If it's actually a physical particle, then not only is it translating, moving left, right, in, out, and up, down, it can actually rotate. And if it rotates about one axis, there's a kinetic energy associated with that axis, and that would be 1 half I omega squared. If you rotate it about a different axis, then that's another 1 half I omega squared, but there's a different I and a different omega. And then, of course, you could also rotate about a different axis, and that would be a third term, 1 half I omega squared. So these terms could be three, four, five, six different terms being represented by one. Not only that, some people will disagree. Like as I was telling you, I generally think of the energy stored in a spring not as potential energy. I often think about it as work in or work out. So occasionally, if I have a problem that involves something running into a spring or something compressing a spring and then allowing the spring to expand, I put it in work in or work out. But other people might put it in U initial or U final, and then other people still might put it in E loss. And that's certainly fine, long as you're only counting it once. It doesn't matter where you put it. You just got to make sure you count each source of energy one time and one time only. Now, another thing about this is I'm trying to pull up the chat, so in case anybody asks me a question by chatting, I'll see it. Okay, I got it now. Another thing is the way you write these terms out. You might know, for instance, if you calculate the work done by friction in stopping a car, you probably have realized that that normally turns out to a negative amount of work or a negative amount of energy. You don't put negatives in this equation. So if you're using this version, like I've taught, like I'm teaching you, the only time you ever use a negative is when you're using this particular equation right here. So keep that in mind as well. So do whatever it takes to memorize these facts I've told you about here, and I think you'll find that this version of conservation of energy is really pretty straightforward and super helpful. And it's different from the ones that the author gives you, which I'll list right now. So the author gives you delta U plus delta K is equal to 0. Now, you could also, since delta U is U final minus U initial, you can also write that as U initial plus K final, K initial, excuse me, is equal to U final plus K final. That's another version. So this is one version the book would use. This is another version the book would use. And then the book also has this version right here, which is delta U plus delta K equals work in C, meaning non-conservative. So what I'm pointing out here is how much these two equations, this one and this one, really look like this. The only difference is it doesn't include that, that, or that. So this equation and this equation are the same thing as this one, except it doesn't have these non-conservative forces. That's why they add this one. And then in that sense, you can sort of think of this work non-conservative. You can sort of think of that as work out minus work in plus E loss. So this W in C would be work out minus work in plus E loss. So that's another way of doing it as well. But you can see in that case, you're going to have pluses and minuses and all this weird stuff. So that's why I've fallen upon this version and used it for literally years while I was a tutor, but then decades since being a teacher. So let's start off with example 8.1, which isn't about conservation of energy. It's more about potential energy. So I just want to run that by you. Example 8.1 is this, and I am using the book examples, so I'll read them to you. It would be helpful if you have access to them by looking at your ebook. But example 8.1 says potential energy changes for a roller coaster. A 1,000 kilogram roller coaster car moves from point 1 to point 2 and then to point 3. Notice in my diagram, I've went ahead and drawn point 1, point 2, and point 3. A, what is the gravitational potential energy at points 2 and 3 relative to point 1? That is, take y equals 0 at point 1. Part B says, what is the change in potential energy when the car goes from point 2 to point 3? And you can see that's how I've written that down for my version of A and B. And then part C, it says repeat parts A and B, but take the reference point y equals 0 to be at 3. So that's what I'm going to do here is I'm going to show you how to work this. So what we're doing here in the first part in A is we're pretending that basically we have set up a coordinate system such that the x-axis would be here and the y-axis would be here, so that y is equal to 0 at position at height 1. That's really what part A is. When we go to part B, then that can be looked at as if this is x and this is y, and this is y equals 0. So that's the part B part, and the red is the part A part. So that's the big difference here. So let me go about calculating this. I'm obviously going to make use of the u equals mgy. So in writing solution, that's what I need to put down. So remember, you should write solution and then you write the equations that you think you're going to be using. If this were on a test, you definitely want to take, maybe you don't take the time to write the word solution, but you definitely write down the equations you think you're going to use. And then somewhere later, you're going to take that equation and substitute the values in for the variables that you know, including their units. And then if you end up not getting the right answer, but you have that, you're still going to get the lion's share of the points just by choosing the right equation, putting the numbers in with the right units and that sort of thing. So that gets you a good share of the credit automatically. Additionally, if you draw diagrams, that can help me give you points and partial credit and stuff like that. So keep that in mind when you're doing the test. So my potential energy that I'm using here is mgy. So for part A, U at 2 is going to be M, which is 1,000 kilograms. Notice I made it such that it's 4 sig figs by putting the dot zero after it and put an underscore there. And then G is 9.80 meters per second. So that's 3 sig figs. And then if I treat elevation 1 as y equals 0, then the height at 2 is just 10 meters. And therefore we get 9.80 times 10 to the fourth joules is the potential energy at 2. The potential energy at 3 is 1,000 kilograms. I'm going to leave the units off here because you can see how much of a pain that is, times 9.80. Now, in this case, the y value is actually negative. So it's negative 15.0. And now if I do this calculation, which I got to get my calculator out, we're going to do 1,000 times 9.8 times 15, and that gives me negative 14, negative 147,000. So this is negative 1.47. And technically that's 3 sig figs, but the next digit is 0. I just put it there so we know what we're doing. So this is negative 1.470 times 10 to the fifth joules. So that's what part A was asking us for. So I'm going to say this is equal to U at 2, and this is equal to U at 3, and I'll circle those both. And we realize that's the answer to A. Now for part B, they want us to calculate the change in potential energy. So delta U, and I'll write this as 2 arrow 3, which means I'm saying this is the potential energy change in going from 2 to 3. And the delta, which means change, that always means final minus initial. So technically, this should be U at 3 minus U at 2, which obviously U at 3 is negative 1.470 times 10 to the fifth joules minus 9.80. And just to be consistent, I can put another zero on the end of that and underline it, times 10 to the fourth joules. Now, doing this math, I'll get the change. That didn't work. So I'm taking negative 1.47 times 10 to the fifth, and I'm subtracting from it 9.8 times 10 to the fourth, and that gives me negative 2.450 times 10 to the fifth joules is equal to delta U 32. So that's the change in potential energy and going from 2 to 3. Now for part C, I'm supposed to do the same thing, but treating it with as if we're using the green coordinate system so that y equals 0 at an elevation of 3. So to do that, I'm going to calculate u at 2. Now notice the height above 3 at point 2 is 15 meters plus 25 meters. So that's going to be 1,000 times 9.80 times 25.0, and that gives me 1,000 times 9.8 times 25, and that gives me 2.450 times 10 to the fifth joules. Now the potential energy at 3 would be 1,000 times 9.80 times 0.0, and that gives me 0. So delta U 2 to 3, which equals U at 3 minus U at 2, is going to be 0 minus 2.450 times 10 to the fifth joules, which gives me negative 2.450 times 10 to the fifth joules equals delta U 2 to 3. So the main point there, hopefully you already realized it, is that notice the change in potential energy did not change just because we looked at two different versions of what y equals 0 means. As I told you, the difference in potential energy or the change in potential energy or the derivative of potential energy is usually the thing that you can measure. It's very rare that you could measure, for instance, the actual potential energy, but you can pretty readily measure the change in potential energy or the derivative of the potential energy. So adding that arbitrary constant, which is what happens when we change the origin from the height of point 1 to the height of point 3, we literally, in going from 3 to 1, we would just literally add a m times g times 15 meters. Okay, so any questions on that? All right. The next question is problem 8.2. So, one of the things we learned was that not only does a conservative force allow us to calculate a scalar potential function that we can use, and that allows us to avoid doing all the vector work, or at least a lot of the vector work. Well, it turns out that you can also find out what the force is once you have the scalar potential, and that was given by that theorem, and it says explicitly the force is the negative gradient of the potential energy function. So that means when you take the derivative of the potential energy function with respect to x, you get the x component of the force. When you take the derivative of the potential energy function with respect to y, you get the y component of the force. And when you take the derivative of the potential energy with respect to z, you get the z component of force. You got to remember, of course, the force is the negative gradient of v though of u though. Okay. So in this question, they're saying, suppose u of x is equal to negative ax over b squared plus x squared, where a and b are constants. What is f as a function of x? So as I said, you're really supposed to be calculating the gradient, and the gradient is you take the I hat and you multiply that by the partial derivative with respect to x. Only in this case, you're going to take the partial derivative of u. So it's I hat times the partial of u with respect to x, and that gives you the x part of the force. If you also had a function of y, then you would say plus j hat partial of u with respect to y, and that would give you both the x part and the y part of the force. If you also had a z in there, though, you could say plus k hat partial of u with respect to z, and that would give you the total force. In this case, we just have a variable x. So it's really only a one-dimensional force that we're worried about, and we're going to calculate what that is. So F is equal to the negative gradient of u, and the gradient is defined to be I hat partial derivative with respect to x. Notice how I left a space between the triangle and the equal symbol, and now I'm leaving a space between the partial derivative and the plus, and then I write j hat partial derivative with respect to y, leaving a space again, k hat partial derivative with respect to z, like that, and I'm leaving a space again. So that's really what happens. So when you put a scalar function to the right of this gradient, it spits out a vector, and that vector is called the gradient vector. So now we can calculate this. We can see that really all the j hat and the k hat terms are going to be zero. So f is going to be equal to, or let me say it this way because I'm going to do it the easy way. I'm just going to say f sub x is equal to the negative derivative with respect to x of u sub x. So that's how I translate those two statements on the line above to what we're doing right now. So what I'm going to do is put a negative out in front, and I'm going to say take the partial derivative with respect to x of negative a times x over b squared plus x squared, like this. And in doing so, we can treat this. What I do is never, ever, ever do I take time to memorize the quotient rule for derivatives. I just know how to derive it from the multiplication rule, and of course, I know how to derive the multiplication rule, and that one's stuck in my head, anyways. But notice I have a constant negative a in the function, and I have a negative out in front. So I'm going to go ahead and pull that out in front and just say positive a. Now I'm going to say the partial derivative with respect to x of x times, let me write this way, parenthesis b squared plus x squared to the negative 1 power. So now that derivative is a little more straightforward for me to calculate. I still have the plus a out in front. Now, I'm going to put that outside of a bracket because now I got to use the product rule. So I'm first going to take the derivative of the first factor and multiply it by the second factor. Then I'm going to say plus, and I'm going to take the first factor and multiply it by the derivative of the second. So the derivative of the first factor is the derivative of x with respect to x, and I just get 1. But now I've got to multiply that by b squared plus x squared to the negative 1 power. And then I got to say plus. Now I'm just going to take the first factor, which is just the plain x, no derivative this time. But now I'm going to take the derivative of b squared plus x squared with respect to x. So I could take the derivative of u to the negative 1 with respect to u, and I would get negative 1 times u, which is b squared plus x squared, raised to the negative 2 power, because you got to subtract 1, right? And then I have to take the derivative of u with respect to x, and u, of course, is b squared plus x squared. So if I take the derivative of that with respect to x, I get 2x. So that's me avoiding doing the quotient rule, but doing the actual product rule for differentiation. And now I'm going to try to make it a little cleaner. So I'm going to get a over b squared plus x squared, like that, plus, well, actually, let me look. It does not look like plus will survive. It looks like the minus will survive. So I'm going to get x times the 2x times the a. So this is going to be 2a x squared in the numerator. All of that divided by b squared plus x squared in the denominator, but that one's going to be squared. So now that's the total function, but I still want to make that a little cleaner. So what I'm going to do is multiply the top and bottom of the first vector, or the first term, by b squared plus x squared. So when I do that, I get, whoa, when I do that, I get a times b squared plus x squared minus the other numerator, which is 2ax squared, and then everything is over b squared plus x squared to the 2 power. Now I just want to distribute that a and see if I can make this answer a little cleaner. So I now have a b squared plus a x squared minus 2a x squared over b squared plus x squared squared. Now, in this case, I can see that everything's got a common factor of a, so I'm going to go ahead and pull that out in front. And then I can go ahead and combine the like terms. Ax squared minus 2ax squared is negative ax squared. So pulling out the a, I just get negative x squared. So that's going to become b squared minus x squared over b squared plus x squared to the 2 power. And that's equal to f sub x of x. Any questions on that one? All right. Again, if the function had x's, y's, and z's, then you'd still have to compute that partial derivative. And I know you guys haven't had partial derivatives unless a couple of you might have actually already had Calc 2 or Calc 3. It's normally not introduced until Calc 3. The big deal is it's not any different than a regular derivative. You're just going to pretend like all the variables other than the variable you're differentiating with respect to, all those other variables are just constants. So if you treat them like constants, then you're going to be able to easily work it out. And therefore, if the function u was not just a function of x, but a function of x, a function of y, and a function of z, then you could get a three-dimensional force component, because you'd have one component that comes from the derivative with respect to x, another that comes from the derivative with respect to y, and another that comes from the derivative with respect to z. Hopefully that makes some sense. All right, so let's go on. Your book does tell you these bold print things about ways of determining whether a force is conservative or not. Those are things that you should know. Those are typical conceptual questions. It also has a little caution, and it says, caution, it is delta U that matters. And that's what I was talking about earlier. The change in potential energy is something we can measure, whereas the regular potential energy we usually can't measure. So an additive constant to it doesn't matter at all. I'm going to move on to a further problem. So let's look at example 8.3. Example 8.3 says falling rock. If the original height of the rock in figure 8.7 is y1 equals h equals 3.0 meters, calculate the rock speed when it has fallen to 1.0 meters above the ground. So let me go ahead and show you how to do this problem. This is example 8.3, and it's called Falling Rock. And what we're picturing here is a rock that is a height of 3.0 meters is equal to h, but that's also going to be equal to y1. And we're going to drop that rock. And what we want to figure out is it's going to move down, down, down. And then this position is 1.0 meters, which is equal to y2. Okay. And what they want to know is at this point, v final equals question mark. So that's really what they're asking here. They didn't give us the mass of the rock or anything. So all we've been given is this sort of diagram and this distance, and they want us to calculate the speed when the object is 1 meter above the ground. So what I'm going to use here is solution U initial plus K initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. In this case, there's not any air resistance, which could be interpreted as a E loss, or maybe someone might work some way of calling it a work out or something like that. There's no one throwing it, so I can't calculate a work in. There's no one catching it, so I can't imagine someone's putting work in it to slow it down. I can't imagine a friction force or anything. So what that means is, in this case, the work in is zero, the workout is zero, and the E loss is zero. And this is a big part of conservation of energy. Once you write down the equation, then you discover that a lot of the terms are going to be zero, and that's just great because that means less work. Now, the other thing is normally what you'd say is the potential energy is initially very high, but the kinetic energy is zero, and that's what's going on here. So I'm going to go further and say that the initial kinetic energy is zero. Now, I could also say that the final potential energy was zero if I wanted to, uh, and that would be just fine. But it's sort of this the way they worded this question is they might want to later know what's the velocity when it gets to the ground, in which case it just felt kind of ugly calling y equals zero to be the height of y2. So I'm just going to treat y equals zero to be the ground level right here. Okay. But that being said, I could have done it the other way and I'd still get the right answer. So now that I've got all this, that means my final potential energy is not going to be zero because I chose the y equals zero at that lower point. Now all I have to do is put in mg y1 plus 0 is equal to mg y2 plus 1/2 mv final squared plus 0 plus 0. Now what you see is there's a common factor of m on both sides of the equation, on every term in fact, and since it's on every term, that means we can divide it out, and what we get instead is now gy1 is equal to gy2 plus 1/2 v final squared. And we could actually solve for that, and it looked kind of neat. In fact, I'm going to do it just so you'll see that, oh, wow, this looks a lot like one of the kinematic equations that we used earlier to solve similar problems. And in fact, what you get is Vf squared is equal to 2g times y2 minus y1. Notice how that looks a little bit like v squared equals v0 squared plus 2ax minus x0. It's the exact same equation, except of course we don't have an initial velocity and we're doing it in the y direction. So with all that in mind, we can go ahead and calculate it. I'm just going to put the numbers in instead of taking the equation that I got over here to the right. So I'm going to say 9.80 times y2, which is 3.0, I'm leaving the units off again, is equal to 9.80 times 1.0 plus 1 half v final squared. So 9.8 times 3 is, I think, 29.7, or excuse me, 29.4. So this means 29.4 is equal to 9.80 plus 1 half v final squared. So I can subtract 29.4 minus 9.8, and that gives me 19.6 is equal to 1 half VF squared. And that means VF is going to be the square root of 2 times 19.6. So V final is actually going to be equal to taking the square root of 39.2, and that gives me 6.26. Now, we only had two sig figs, and I wasn't paying close attention to the sig figs, how they worked out, but it does look like I should still have two sig figs. So I'll just put an underline in there. But just know that I didn't do the requisite work to make sure. What I'd really have to do is make sure that when I added 29.4, or when I subtracted 9.80 from 29.4, that I still had three sig figs. It does look like I did because I got 19.6. And it looks like you'd only have three if you had two decimal places, but because the 29.4 had such a big whole number part, the three sig figs was still covered by the 19.6. And then you just multiply that by two, so it does get three sig figs. So I'm not going to leave that underlined. I'll go ahead and erase it because it does look like it worked out. Anybody have any questions on that? Now, notice there is a little ambiguity here because technically you could take the positive or the negative square root, but that was a problem we had before when we were using v squared equals v0 squared plus 2ax. That's what I was telling you why I said some college and some physics instructors just don't allow their students to use that at all because it's not a vectorial equation, and therefore you have to make a physical hypothesis as to when you solve by taking a square root, if it's going to be the positive square root or the negative square root. Let's move on now. Now we're going to go to example 8.4. And example 8.4 says roller coaster car speed using energy conservation. Assuming the height of the hill in figure 8.8 is 40 meters and the roller coaster car starts from rest at the top, calculate A, the speed of the roller coaster car at the bottom of the hill, and B, at what height will it have half this speed? Take y equals 0 at the bottom of the hill. So I'm going to go ahead and draw the hill, if you will. And it looks like the hill goes something like this, and then comes back down, and then comes back up to more or less the same height. That's the key thing here. They're going to say that this elevation from here to here is 40 meters, and I actually took the liberty of adding an extra sig fig to it. And we're going to take this distance as y equals 0 there. And what they want to know is A, the speed of the roller coaster at the bottom of the hill, and then B, they want to know at what height at what height it will have half its speed. So y equals question mark if V equals 1 half V bottom. So that's the other part of the problem. Solution. This is again a case where we're ignoring air resistance and friction, and there's no springs to compress. No one's giving it a push initially. No one's stopping it by applying work to it, or there's no air resistance sucking energy out. So again, we're going to have work in and work out, and E loss equals zero. But it's U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. So all of those I just explained are zero. And not only that, for part A, we can do some other stuff. So let's say part A, we're going to say U initial is M times G, and I'm just going to call this Y. So that's mgy. The initial kinetic energy is also zero, so I'm going to put a zero there. And then I already said the Wn was zero, so I'll put that there just so you'll know what's going on. Now, when it gets to the bottom, the potential energy is going to be zero because I'm taking y equals zero at that height. So that's a zero. But what I do have is 1 half mv final squared, and then plus zero, and then plus zero. So you can see that again, I have a common factor of m that I can divide both sides by. And then luckily, the math didn't matter because it all canceled out. If it mattered, then it wouldn't cancel out, and we need to know it to solve the problem. But in this case, I'm going to get V final, which equals V at the bottom, is actually equal to 2GY square root. So I'm going to take the square root of 2 times 9.80 times 40.0. If you worked out the units, you'd see that that does work out to be meters per second. So I'm going to take square root, as soon as I find my square root function. Oop, there it is. Square root of 2 times 9.8 times 40, and that gives me 28, which is really nice. So V bottom is equal to 28.0 meters per second, and that's part A. Does that everybody follow that? Anybody have any questions? Now, what we want to know is what is the elevation at which the velocity will be half that. And you actually could, in principle, well, you're actually going to get it, but the height could represent two different places on the track. So just keep that in mind. So in part B, we're going to do it as follows. Again, we have U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. So again, those are going to be 0, 0, and 0. This time, we're not actually going to a potential energy equal to 0. We're going to a potential energy equals whatever it has to be so that the velocity is now half as big as 28 meters per second. So the initial kinetic energy is going to be 0 again. The final kinetic energy or the final potential energy will not be. So in this case, I'm going to have mgy plus 0 is equal to mgy2 because y2 is what we're really looking for here, plus 1 half m. Let me write this as v bottom. So I'm going to put v bot over 2 quantity squared plus 0 plus 0. Again, you can see that there's a common factor of m that can disappear. So that's going to take out that and that and that and that. So now we're going to get gy is equal to gy2 plus 1. Now remember it's 1/2, but when I square v bottom over 2, that's going to become a 4 in the bottom, and 4 times 2 is 8. So now I've got 1 over 8 here, v bottom squared. And the y2 is what we're wanting, so I'm going to say gy minus 1/8 v bottom squared is equal to gy2. So I can say y2 is going to be gy minus 1/8 v bottom squared, all that divided by g, which is y minus 1 over 8g v bottom squared. So now I can plug these numbers in, and that is 40.0 minus 1 over 8 times 9.80 times 28.0 squared. So this should give me y2 is equal to 40.0 meters minus, now I'm going to take the 28 and I'm going to square that. And now I'm going to take that and divide it. That's 784, by the way. I'm going to take that and divide it by parenthesis 9 or 8 times 9.80, close parenthesis. And lo and behold, 784 divided by 8 times 9.8 gives me just 10. So I get 40 minus 10.0 meters equals 30.0 meters, and that's y2. So that's our answer for part B. Notice that means that when the train car, when the roller coaster car comes down just a single 10 meters lower than the top, it's already reached half the speed that it's going to have at the bottom. So that's kind of a neat thing to figure out, just knowing that the velocity is going to reach that high that quickly. Anybody have a question on that? All right. Your book does a really nice conceptual example. I think I'm going to do that one, and then I'm going to do a beast of all examples to show you how to best use this crazy equation version that I gave you. So, looking at conceptual example 8.5, this says speed on two water slides. Two water slides at a pool are shaped differently but start at the same height h. Two riders, Paul and Jeannie, start from rest at the same time on different sides. A, which rider, Paul or Jeannie, is traveling faster at the bottom, and then B, which rider makes it to the bottom first. Ignore friction and assume both slides have the same path length. Okay, so let me give you a little bit of drawing of this just in case you aren't looking at your book. So this is going to be example, and it's really a conceptual example, 8.5. What we have here is a slide that goes like this, and then there's another slide that goes like this. Oops, made a little bit of a boo-boo there. Okay, so now this other slide goes like this and comes out like that. So that's sort of a drawing of it. The main thing is both of them have the exact same height, and that height is y or h or whatever you want to call it. I called it y. And what we have is stick figure up there named Paul, and then we have stick figure over here named Jeannie. Now, the big thing to understand here is if you look at the equation, we have U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. And they told us to ignore friction and all that stuff. So again, we're going to get rid of those extra things, which again makes it seem a little self-defeating, but the next example is going to show you better. The main thing here is the initial potential energy of Jeannie and Paul, UI for Paul, is equal to M Paul times G times Y, and UI for Jeannie is equal to M Jeannie times G times Y. Additionally, U final for Paul is equal to M Paul times G times 0, and U final for Jeannie is equal to M times Jeannie, M of Jeannie times G times 0, which also equals 0. So the change in potential energy depends on the two masses, but what we also got to realize is the initial kinetic energy Ki for Paul is equal to 0, and the initial kinetic energy Ki for Jeannie is equal to 0, and the final potential energy K final for Paul is equal to 1 half M Paul V final Paul squared, and the final kinetic energy for Jeannie is 1 half M J times V final sub J squared. So with all of that, what we can figure out is that we're going to have M Paul G Y equals 1 half M Paul V final Paul squared. You can see automatically that the masses cancel out, and you're going to get V final Paul is equal to the square root of 2 times G times Y. Now, in working the Gini case, you got M Gini times G times Y is equal to 1 half M Gini times V final Gini squared. Again, you can see that the masses cancel out. And again, you see that V final Gini is actually equal to the square root of 2GY. So that tells you that the first question, A, which rider, Paul or Genie, is traveling fastest at the bottom? Clearly, that means they're both traveling at the same speed. So for part A, Paul and Genie are traveling at the same speed at the bottom. Now, for part B, it says which rider makes it to the bottom first. Well, what you realize in looking at Genie's track is Genie is at all times lower than Paul is. So the fact that immediately they could start like right next to each other, let's say right here, they could both start next to each other at the same height, but immediately Genie starts to go down, and as her height changes going down, the potential energy is dropping, and the kinetic energy is going up by the exact same amount that the potential energy drops. So she's immediately going faster, and she's just right there. When he gets here, she might be right here, or as luck would have it, since she's going faster, there's a good chance she might even be, when he's here, she might be out in front of him here. And then when he's here, she might be further out in front of him. But the main thing is at all points, Jeannie's kinetic energy is higher than Paul's because Jeannie is at a lower height and therefore more of her kinetic energy has been made out of the loss of potential energy that she got to quicker. Because of that, you can see that at every point on this track, Jeannie's going faster, so she should make it first. Because So I ended up writing it in sentence form from there, or equation form from there. It says Jeannie will make it to the bottom first because at all points Jeannie is lower than Paul, so that U for Jeannie, the potential energy for Jeannie, is smaller than the potential energy for Paul at all points. Since the potential energy is smaller, that means kinetic energy of Jeannie is higher than the kinetic energy of Paul at all points. And since kinetic energy is 1/2 mv squared, that means the velocity of Genie is higher than the velocity of Paul at all points. And since it was higher velocity at all points, then clearly she would be going faster at each point and cover. Since he's claiming that the assume that both sides have the same path length, then you can reach the conclusion that she's clearly going to cover that distance in a smaller amount of time. Anybody have any questions on that? Okay, so there's a lot of good other examples. There's a toy dart gun. There's a cool one with some girl doing some kick butt pole vaulting and all sorts of cool stuff like that. There's a pendulum, there's a ball falling on a spring, all of that. There's a yeah, swinging pendulum. All of those are pretty straightforward. I don't see anything really major jumping out as a major educational difference from what we've been talking about. So I think it's best that I just jump into showing you an example using this equation in such a way that we're going to investigate each of the terms. So I'm going to make up a problem. It's the same problem I make up just about every semester, and it's wildly inappropriate in the sense that I make it with such horrible numbers that poor child is going super fast and really in a lot of danger. But let's begin that. So Mr. Younger's example. So what we're going to imagine here is we have a mountain and it's nice and level at the top, and then there's a slope going down and down and down like that. Uh, Actually, I think I need to make it smaller. So I'm going to say it goes down like that. Yeah, that'll work. Okay. So first off, that blue line there is supposed to be horizontal, even though it doesn't look horizontal. So we're assuming that's horizontal. I'm going to say this height is 100.0 meters. And I'm going to say we have a little girl sitting on a sled like such. Okay. And we have a dad pushing with a force of 100.0 newtons at 30.0 degrees below horizontal, and he is in fact going to push her for a distance of 3.00 meters. So that's dad back there pushing the little girl, but he's pushing down at an angle of 30 degrees. So we got to figure out the component of force parallel to the displacement, of course. And then she's going to go down this incline. And when she gets down to the bottom of the incline, right at the bottom, there's a rumble strip that's been made for the safety of kids so that they can hopefully start slowing down before they get to the wall. Okay. I'm going to say this distance right here is 20.0 meters, and the kinetic coefficient of friction is 0.300. Okay. And then after that, if the person actually makes it through the rumble strip with more velocity than zero, then it's going to keep on going and it's going to run into a cushion. And that cushion is connected to a spring mechanism. And in principle, we'd like to know what distance the spring would be compressed if the spring constant is 15,000 newtons per meter. I'm going to say the mass of the girl plus sled is equal to 75.0 kilograms. And the questions I'm going to ask are the following. V1 equals question mark. So once she gets down to the bottom of the hill, I'm curious, hey, how fast is she going? Right? Then the next question I'm asking is how far will the girl make it across the frictionful rumble strip there? So in other words, we've set up this rumble strip to try to slow them down, not unlike a safety ramp that you see in the mountains. I think they call it a runaway truck ramp or something like that. This is sort of like that. And in principle, the reason why they do that with trucks is it's really deep sand and the truck almost comes to a stop immediately. It goes a good distance because it's so massive and going so fast. But the big thing is you've put it there, and in principle, if it's enough friction, it could bring it to a stop. If it is enough friction, I'm curious what is the distance x1 that she goes before she comes to a stop. If, however, I do that calculation and find that she can go the full 20 meters, then that x1 is completely moot. At which point, I then would like to know right here what is the velocity v2. In other words, if she really made it through all 20 meters, then she's going to come out of that rumble strip moving with some velocity, and the height's not changing, so she should still have the velocity from the end of that rumble strip all the way to hitting the bumper, and that velocity is what I want to know. So I'll find out that, and then knowing that she's going to run into that cushion at that speed, I would like to know how far she's going to compress the spring to bring it to a stop. Okay. Uh, so that's the big problem, and we're going to do it all with conservation of energy. So again, we're going to use U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. And this one, like I said, it's just a problem I've made up that allows me to use each of the terms. And it's not necessary that you use the terms the same way I do. What one person calls E loss, another person might call work out. And what one person calls work out, another person might call E loss. And again, what another person might call work out, some person might call the final potential energy. So the 1/2 kx squared, for instance, could go into that. So let's go ahead and start calculating one by one. I'm going to calculate V1, then I'm going to calculate X1, or see if I even need to calculate X1, and then I'm going to calculate V2, and then I'm going to calculate what actually X2 is. And of course, getting V2 and X2 depends totally on X1 being moot. And I think I've made these numbers so gigantic that X1 will be moot. So let's do that. So I'm going to put in all the numbers I know. For starters, I'm going to calculate work in as if it's what the father did. So work in is going to be, I take the father's force, which is 100.0 newtons, and I multiply it by the distance, which is 3.00 meters. Remember, I'm using the dot product here. So work in this case is F dot D because the force isn't changing angle or magnitude anywhere over the displacement. So it's just F dot D. And F dot D is F times D times the cosine of the angle between them. And if you look, the angle between them, if you put the displacement vector and the force vector tail to tail, the angle is in fact 30 degrees. So if I take 100 times 3 times cosine 30, I get 259.8 joules. Okay. I'm carrying way many extra credit, extra sig figs here. I don't care. I'm just going to run with it. Okay. Uh, I would also recognize that when I'm down at the bottom, the friction force is going to equal mu k times the normal force. And the normal force, since it's perfectly horizontal, is just going to be mg. So I'll be making use of that as well. And then E loss is going to be basically the friction force times the distance x. And those two, the displacement is horizontal and the force of friction is horizontal backwards. So if anything, it should come up negative, but no cosine is necessary because it's the cosine of zero. And of course, I told you, you never put a negative number in there except for when using that U equals negative G M M over R. So now I'm able to go with this. I'm going to go ahead and write it as U initial is 75. I'm going to leave off the unit 75 times 9.80 times 100.0. That's my U initial. My kinetic energy initial is 0. My work in is 259.8, like that. And then notice I'm running out of space horizontally. I'd run into the diagram, so I'm putting the equals down here. And then U final at the bottom is going to be 0 because it's M times G times the height of Y equals 0, which is what I'm saying for this height. And then the kinetic energy is really what I'm talking about for part A. So this is 1 half times 75.0 times V1 squared. So that's all I need. If I multiply 75 times 9.8 times 100, that gives me 73,500 plus 259.8 is equal to 37.5 times V1 squared. That means V1 is going to be equal to, so I take the 73,500 and I add to it 259.8, and that gives me 73759.8 is equal to 37.5 V1 squared, and that means V1 is equal to, I'm going to take that, divide it by 37.5. Hopefully I'm doing my math correctly and thinking that's half of 75. And that gives me 1966.928. So V1 is the square root of 1966.9, and that gives me a really, really large velocity, 44.35 meters per second is V1. So we know that she's moving about 90 miles per hour as she gets down to the bottom and runs into the frictionful area. Now, the big thing is I'm really reusing this equation over and over again, but I should be smart about it. I've just figured out what the whole left side is. There's no need for me to recalculate that. So in figuring out what X1 is, what I'm going to do is calculate the total E loss from going that whole distance of 20 meters. And if I see that smaller than the 73,759.8, then I know it's not going to make it. By the way, it's now 6:50, so you guys are free to split if you need to. I completely understand. I'm just going to finish this out and then kill the video and ask for questions if anybody has them. But I'm just going to go ahead and finish, so feel free to leave. I'll post this tonight. I'll make sure I do it tonight instead of in the morning. So thanks for coming, everybody. I'm going to continue on with this problem, and that's supposed to be equals V1 there. Okay, so now for is X1 equal to 20.0 meters large enough to stop her? That's what I'm trying to figure out. Well, E loss is supposed to be the friction force, which I've already told you was mu k times the normal force times the displacement times the cosine of the angle between them. But the cosine of the angle between them technically is 180, but that just gives you a -1, and we don't use negatives. So in this case, I'm going to say 0.300 for mu k. The normal force, because it's horizontal, is just mg, so that's 75.0 times 9.80, and then times the distance would give me 20.0 meters. Now, if I happen to find that this amount is larger than 75,759, then I know that she didn't make it to the end, and I have to go back and calculate at what value of X1 is this equal to 73,759. But that's not going to happen, so you can tell that we are just going as it is. So zero point 0.3 times 75 times 9.8 times 20 gives me 4,410 joules, which is less than 73,759.8 joules. So X1 is moot. In other words, it's just an academic question that has no bearing here because clearly there was way too much energy. Now I can go to the next part, which is figuring out what the velocity V2 is. So again, I'm not going to go back and recalculate everything. I'm just going to use the values that I found. So I have 73,759.8. That's going to be equal to, that's the whole left side. The right hand side, I've already got rid of the potential energy, so that's gone. But I do have some kinetic energy after she's made it through the rumble strip. So the U potential energy is 0, so I'll put a 0 there. The kinetic energy is not 0. That's going to be 1/2 times 75.0 times V2 squared. And then the workout, I haven't used that because I plan on using that for the 1/2 kx squared for compressing the bumper. So I'm going to say plus 0. And what I am using is the E loss, and that E loss we calculated was 4,410. So now I can go ahead and solve for V2. And what I do is I take my 73,759.8 and I subtract from it 4,410. That gives me 69,349.8. And now I'm going to multiply that by 2 and then divide by 75 and then take the square root. So I'm taking my 69,349.8 and I'm multiplying that by 2. Now I'm dividing that by 75. And now I'm taking 138,699.6. 138,699.6. I'm dividing that by 75. That gives me 1849.3. And when I take the square root of that, I get 43.00 meters per second equals V2. So she's still going to hit that cushion, which thank goodness it's a cushion, but she's still going to hit it at very close to 90 miles per hour. She's only dropped a speed of 1.35 meters per second, so she hasn't slowed down very much. Now all I'm going to do is use all this information to figure out what exactly is the X2. In other words, how far is she going to compress the spring to bring her to a stop? To that end, I'm going to go ahead and take the 73,759.8. That's equal to zero potential energy plus zero kinetic energy now because we're actually going to compute it till she comes to a complete stop. So the kinetic energy is going to be zero. The potential energy is zero. The workout is going to be 1/2 of 15,000 times x2 squared. And then the E loss we already calculated was 4410. So now I can say that x2 is equal to, again, I'm going to take the 73,590, or excuse me, 73,759.8. I'm going to subtract 4410 from that. And now I'm going to multiply by 2. So I've got 69,349.8. I'm going to multiply that by 2. Now I'm going to divide that by 75, or excuse me, by 15,000. And that gives me 9.24. So x2 is going to be the square root of 9.247. And that's going to be 3.04 meters. So that's what she's going to actually compress that spring by. And you can imagine that's a really big distance. That's, about 10 feet basically. And that's it. So hopefully you have some understanding, some appreciation for how this equation works and how all the different terms can come in handy. You guys are free to go. Well, we've completely finished chapter 8 now. Remember, you have a test that's going to be next week. I'm going to make some times where I can proctor it for you, but they're going to be actually probably Tuesday and Wednesday, not of next week, but the week after. So I'm going to probably make 1 or 2 times to proctor you online. One's going to be early in the morning. The other one's going to be in the evening, probably starting like 6:50, 7 o'clock, something like that, 7 p.m. Whereas the other one's going to start at like 7:30 in the morning. Uh, but those will be not after this weekend, but after the next weekend. So you'll get ample time to complete your test. Remember, you have an online test that's supposed to be due by Wednesday of next week, and you definitely should have that done before you take the face-to-face test. And then you're going to have a face-to-face test that has to be done by probably Tuesday, not next week, but the week thereafter. It would normally be due by Sunday, but I always give you a couple of days or two, and I wanted to make sure everybody had plenty of time to plan and get days off work if they need to use my proctoring. So I'll be posting that proctoring time probably tonight or tomorrow. Have a good one, everybody. Thanks for coming. I'll wait for the last person to leave. Appreciate your enthusiasm, Michelle.
Thank you. Have a great night.
You too. Dang, that was quick. Everybody's out of here. All right, so I guess that's it. Bye bye.